This is question 3 from the 2011 paper, and this question is all about explosives and how explosives work. The question starts with an introduction into explosives and shows us the skeletal formulae of two common explosives, TNT and RDX. It states that some high explosives have a general formula of CaHbNcOd. The key thing is that for an explosive to work, the oxidizer, which is the oxygen atoms, and the fuel, which is the carbon and the hydrogen atoms, are all present in the same molecule. The nitrogen atoms are present in explosives, so that there is the highly exothermic production of hot nitrogen gas. Part A of the question asks you to find an expression for D in terms of A, B and C that must be satisfied for an explosive of general formula CaHbNcOd to decompose to form carbon dioxide, water and nitrogen only. To answer this question, we need to begin by writing out a simple equation to represent the reaction taking place. Now on the left hand side of the equation we need to write the reactants. Now the reactants are clearly the explosive, our CaHbNcOd, and we know that we don't need to add anything else to that side of the equation because of that statement, the oxidizer and the fuel are present in the same molecule, i.e. we don't need to add any extra oxygen into the left hand side of the equation. The products from the reaction are carbon dioxide, water and nitrogen only. We now need to balance the equation, and we can do this simply by balancing each of the atoms in turn. Looking at the carbon atoms, we have A carbons on the left hand side, and so we must produce A molecules of carbon dioxide on the right hand side. We have B atoms of hydrogen going into the equation, and so we must produce B divided by 2 molecules of water, because each molecule of water contains 2 hydrogen atoms. Finally, looking at the nitrogens, we have C nitrogen atoms going into the left, and so we must have C divided by 2 molecules of nitrogen gas produced in the reaction. We now need to balance the oxygen atoms, and this is quite simple, again using the same procedure. We have D atoms of oxygen going into the equation, and we produce 2A molecules of oxygen in our atoms of oxygen, in our carbon dioxide, and B over 2 atoms of oxygen in our water. And if the equation is balanced and the explosive decomposes to form purely carbon dioxide, water and nitrogen, then we know that D must be equal to 2A plus B over 2. The question now moves on to explain the meaning of the term oxygen balance of an explosive and how it can be calculated. The oxygen balance of an explosive is the mass of oxygen which can either be in excess or in deficit of that required for the complete oxidation of carbon and hydrogen, i.e. it tells us how much oxygen is present in the molecule compared to the amount needed for the complete combustion of all the fuel in the molecule. It's expressed as a percentage of the molar mass of the explosive. Part B asks you to write a general expression for the oxygen balance of the explosive CaHbNcOd. Remembering that the mass of a substance in grams is given by the number of moles of that substance times by its molar mass in grams per mole, we can initially calculate the mass of oxygen in our explosive CaHbNcOd using that equation. The number of moles of oxygen can be represented by D, and the molar mass of oxygen is 16 grams per mole, and so we can say that the mass of oxygen in our explosive can be represented by 16D. The mass of oxygen required for the complete combustion of the explosive is effectively the mass of oxygen on the right-hand side of the equation that we wrote in part A, because that equation represents the complete combustion of all the oxygen, or the complete combustion of all the fuel in our explosive. And so we can use the equation again to calculate the mass of oxygen needed for the complete combustion. We generate A moles of CO2, each molecule of CO2 containing 2 moles of oxygen, and so the mass of oxygen in A moles of CO2 can be represented by 2A times by 16. We generate B over 2 moles of water, each molecule of water containing 1 mole of oxygen, and so the mass of oxygen in our B over 2 molecules of water can be represented by B over 2 times 16. So we can represent the mass of oxygen needed for the complete combustion of our fuel as 16 times 2A plus B over 2. The difference between these two values is effectively the top half of our equation, and so the difference between the two values is 16B minus 16 lots of 2A plus B over 2. The question tells us that the oxygen balance is expressed as a percentage of the molar mass of the explosive. We can again use our equation that mass is equal to moles times molar mass to calculate the molar mass of our explosive. The equation for our explosive is CaHbNCOD. This tells us that it contains A moles of carbon, each with a mass of 12. It contains B moles of hydrogen, each with a mass of 1. It contains C moles of nitrogen, each with a mass of 14. And it contains D moles of oxygen, each with a mass of 16. And so we can simplify the molar mass of our explosive to 12A plus B plus 14C plus 16D. Therefore, if we want to calculate the oxygen balance of our explosive, we simply need to divide the difference between the values by our molar mass of our explosive, and then remember to times by 100%. And so if we do this, we end up with an equation that looks as shown there in purple. We can take out the 16 from the top to turn the equation into 16 lots of D minus 2A minus B over 2, because we've got minus outside the brackets, divided by our 12A plus B plus 14C plus 16D, and then remembering to times by 100% to turn it into a percentage. In part C of the question, you are asked to calculate the oxygen balance for RDX, whose structure is given at the start of the question. This can be calculated using the answer to part B. In order to use this equation, it is necessary to determine the molecular formula of RDX from its skeletal formula. If you have not come across skeletal formulae in your studies, at each junction between the bonds and at the end of each bond, it is assumed that there is a carbon atom. So on the drawing of RDX on the question paper, I can highlight in pink where there's a carbon atom. In addition, the hydrogen atoms are not drawn in. It is therefore important that when determining the molecular formula from a skeletal formula, that you add in the correct number of hydrogen atoms such that each atom has the correct number of bonds, i.e. each carbon atom must have 4 bonds. So we can draw into our structure here the correct number of hydrogen atoms such that each of those pink carbon atoms has 4 bonds coming off it. It is actually best to draw out the structural formula of the molecule and then count up the number of carbon, hydrogen, nitrogen and oxygen atoms. If we do this, we can determine the molecular formula of RDX as C3 H6, N6 and O6. So in order to substitute these values into our equation from part B, we can say that A is equal to 3, B is equal to 6, C is equal to 6 and D is equal to 6. To complete the question, it is now simply a matter of substituting each of these values into the equation. If we do this, then we can say that the oxygen value balance for RDX is equal to 16 times D, which is 6, minus 2 lots of A, so 2 times 3, minus B, which is 6 divided by 2, and all of that has to be divided by 12 times 3 plus 6 plus 14 times C, which is 6, plus 16 times D, which is equal to 6, and then all of that has to be times by 100%. And if we plug that sum into our calculator, making sure that we use appropriate brackets where needed, we end up with a value for the oxygen imbalance for RDX of minus 21.6%. The final part of the question describes what happens if an explosive does not contain enough oxygen. If this is the case, there is incomplete oxidation of the carbon and/or hydrogen. For nitrated aromatic compounds, the products can be determined by following a set of rules which are given by a series of bullet points. Part D of the question asks us to apply these rules to determine the products from the explosion of TNT, the structure of which is shown at the start of the question, and hence to use this to write an equation for its explosion. Once again, our first step is to determine the molecular formula of TNT from its skeletal formula. Drawing out the structural formula of the TNT molecule, we can determine that its molecular formula is C7H5N3O6. Before proceeding, we can check that it does not contain sufficient oxygen for complete combustion by looking back at our answer to Part A. In Part A, we determined that for the complete combustion, the number of atoms of oxygen, which was given by D, which was equal to the number of atoms of oxygen, had to be equal to 2 times A, where A was the number of atoms of carbon, plus half of B, where B was equal to the number of atoms of hydrogen. If we do this quick sum for our TNT here, the number of atoms of oxygen is 6, and we can see that is much smaller than 2 times 7, which is 14, plus B divided by 2, so 5 divided by 2. And so we can see that our TNT doesn't have sufficient oxygen to undergo complete combustion. As TNT is a nitrated aromatic compound, we can follow the rules to determine the products from its explosion. Let's follow each of those bullet points in turn to determine the products from the combustion. If we follow the first bullet point, it says that all the carbon atoms react with the available oxygen to form carbon monoxide. Now we've got 7 carbon atoms but only 6 oxygen atoms, which means that we must form 6 molecules of carbon monoxide, and we've got 1 carbon atom left over. The second bullet point says that the nitrogen atoms combine to form nitrogen gas. So we've got 3 nitrogen atoms in TNT, and so they must combine to form 1.5 molecules of nitrogen gas. However, this isn't the end of the story. If we look now at the third and the fourth bullet points, we get some more information. The third bullet point says that of the carbon monoxide molecules formed, 1/3 of them are converted into carbon plus CO2. So we've got 6 carbon monoxide, so 1/3 of that is 2, So 2 of our carbon monoxide molecules are converted into carbon plus carbon dioxide. In addition, from the 4th bullet point, we can see that a 6th of the original carbon monoxide, so in our case that is a single carbon monoxide molecule, reacts with any available hydrogen in the compound, of which we've got plenty, to form carbon plus H2O. So we now need to put those modifications into our initial equation. So let's just go through that. We've got our TNT, which is C7H5N3O6. That initially we said produced 6 carbon monoxide, but we've reacted 2 and a further 1, so 3 of those. So we're left with 3 carbon monoxide plus our carbon plus our 1.5 nitrogen. And then we now need to add in the products that we've determined from points 3 and 4. So we've got some more carbon plus some carbon dioxide plus another carbon atom plus a water molecule. So we can begin to see that we're forming the complete equation. The last thing we need to do is look at balancing the hydrogen atoms. We've got 2 hydrogen atoms in our products and 5 hydrogen atoms in our reactant there, which means that we also need to add another 1.5 molecules of hydrogen gas to our products. And if we do that, we end up with the complete final equation for the explosion of TNT, as our C7H5N3O6 reacts to form 3 carbon monoxide, 3 carbon atoms, 1.5 nitrogens, 1 carbon dioxide molecule, 1 water molecule, and 1.5 molecules of hydrogen. The last part of the question, part E, asks us to calculate the mass of TNT that will explode to produce 1.0 decimeters cubed of gas at room temperature and pressure. In order to do this, we need to use the equation for the explosion of TNT that we produced in part D. At room temperature and pressure, of the products from this reaction, the 3 moles of carbon monoxide, the 1.5 moles of nitrogen, the 1 mole of carbon dioxide, and the 1.5 moles of hydrogen will be gases. And so we can see that 1 mole of TNT reacts to produce 3 plus 1.5 plus 1 plus a further 1.5, which reacts to produce 7 moles of gas. To use this fact, we now need to find the number of moles in 1.0 decimeters cubed of gas at room temperature and pressure. If we know the molar volume of a gas, we can use the equation that the number of moles of gas is equal to the volume divided by the molar volume. Now the molar volume of any gas is given in the question as 24 decimeters cubed at room temperature and pressure. So we can use this value to calculate the number of moles in 1.0 decimeters cubed of gas. So it's 1.0 decimeters cubed, that's our volume of our gas, divided by the molar volume, which is 24 decimeters cubed per mole. And that gives us an answer of 0.0417 moles of gas. So if 1 decimeters cubed of gas is equal to 0.0417 moles of gas, then we can work out that if 1 mole of TNT produces 7 moles of gas, then the number of moles of TNT that must have reacted is equal to 0.0417 divided by 7, because it's a 1:7 ratio, which gives us an answer of 5.95 times 10 to the minus 3 moles. But the question didn't ask us to calculate the number of moles of TNT that reacted. it asked us to calculate the mass of TNT that reacted. So our final stage in our calculation is to turn a number of moles into a mass simply by using the fact that the mass is equal to the number of moles times the molar mass. So I've calculated the molar mass of TNT as 227.14 grams per mole. So we need to take our number of moles, which is 5.95 times 10 to the minus 3. That's our number of moles. We need to times that by our molar mass of TNT of 227.14, and that's in grams per mole, to calculate the mass of TNT that must have reacted to produce our 1.0 decimeters cubed of gas as 1.35 grams. Now this is the answer that is given in the answer scheme, but I think to be completely correct, as we are only given the volume of the gas as 1.0 decimeters cubed, so to two significant figures, we should really only give our final answer to the same degree of accuracy. So our final answer should be 1.4 grams, and that is the two significant figures.